Okay. Hello and welcome. My name is Alvinji Sitampala, matrix number CE200100. So today I'll be presenting PSM2, which my title is Hardware Implementation of Acquisition Layer and Mean Pooling Layer for the CNN digital implementation. So my supervisor is Dr. Chester. I'll go next slide. Okay. So as you can see, this is my objective of my project. The objective is to design and optimize hardware architecture for an activation layer, which is value, and meaningfully lay incident digit acceleration. And the next is to verify the proposed design by comparing the output of the hardware implementation with the software implementation through simulation. And the third objective is to measure and benchmark the performance of the proposed design as compared to the software implementation. Right. So this is the introduction. So what my project is based on is in CNN, which is convolutional neural network. So what my project does is, my project will take a database from the MinSit database. MinSit database has around 70 image of handwritten numbers. So what the input will be is from the MinSit database. For example, as you can see here, this is the input from the MinSit database. This input will go through this AI algorithm. This is the CNN model. You see here, when it passes to the input, it will go to the convolution, then value, then pool, then the reshape, value, and softmax. Lastly, the output should be 2, which the output actually consists of only 10, which is 0 to 9. So my main focus is on the value and mean pool. So what I'll be doing is I'll be creating an architecture design using Kotlin for value to full mean pool. You see here, this is the phase 1, which is MATLAB, the software implementation. So what the MATLAB does is I will run the plot features coding in MATLAB. The plot features produce an data set around each different stages of the CNN. It will produce a data set where that data set is important uh, to verify the uh, output of the quarters, which is the architecture design. We need to have the data set to verify the architecture. So if you see here, what the CNN does is, so this is all the output from the MATLAB. So if you can see here, I pick a number of the MinSit database, which is number 7, as my input. First, it will pass to the convolution filter, then it will create and fill features after it passes to the convolution filter. So what this feature is, what this is the output after the filter. So the convolution filter function is it will detect its specific shape on a number. For example, the input has the you see here it's a shape. It has a long shape on the bottom and a horizontal shape on the upper side, which is number 7. So what the convolution filter does is it will detect either the number 7 has the uh, horizontal, vertical, or other shape on the number 7. So next it will pass through the value. So this part will I'll be focusing the value part. Then this is the output after the value. Then the mean pooling, and then this is the output after the mean pooling. This, as you can see, I placed the convolution plus value plus. Then please do remember that when I said this MATLAB will produce the data set, each data set consists of 400 data. It's a floating point. So what the data set, I mean the MATLAB produce is for one, you can see here for one part, it has a 400 data set. So we got around 20 data in 20 features. So each features will produce data set. Each each pages will produce 400 data. So as you can see, every stage produces a set of data in MATLAB. So first, now I'll be explaining about the value. You see here, this is the value. I'll explain deeply on how the value and mean pooling works. So this is how does the value works. The main function of value is if the input is positive, its output the same value. If the input is negative, its output is zero. That's the function of value. So just now I said that there's MATLAB produce the data. What the data will do is, what the value will do is, it will look for the negative value. If it's negative value, it will become zero. So you can see here on the down part, this is decimal numbers. This is the hexadecimal number. Please to understand why I use the hexadecimal is quarters only can use in hexadecimal. Unsigned value or decimal value can't be used because the output has some changes on it. So for accurate output, I decided to use the hexadecimal value. So the output will also be in hexadecimal. So if you see here on the red highlight, the part that highlighted in red, this is all the negative value. So it will change to 0. If the value is positive, it will remain the same. This in theory should works. So next is the mean pooling. What the mean pooling main function is, it reduces the size of data, shrinks the image. So how the mean pooling works is it's an average. So please to understand mean pooling 2 times 2. 2 times 2 is size of its kernel. Means it only goes 4 data each time. If you see here, so before that, the equation of mean pooling is average, which is 4 data summing then divide by 4. So this is how the mean pooling will work. See here. So this is the second part, 0, and the third part until it go for here. Means it will finish this part, this part, this part until the end. So that's how the mean pooling works. Next, this is the hardware implementation. If you see here, this is the simplified design for easy to understand. So if you see here, feature 1 to feature 20 is the input after the convolution. Please to remember that I take the input after the convolution, not the input of the pixel from the MIXI database. So each, before I said from the MATLAB, produce 20 sets of 400 data. So what I did is every data is saved in a round file. Then it passes to the model. The first is it passes to the value model and the mean pooling model. Then the pool 1 until pool 20 is I saved in RAM. Data is saved in RAM. So now I'm explaining on this value and mean pooling. So this is how the design works. This is how the design is looked. It's a simplified design. Later on, I'll show you the architecture on the quarters. So how this works is you can see the data and indicate the number of, the sets of data. It's got around 1 to 20. So for this, it's 1. So what it does do is the sets of data. The data is 32 bits. So how the value model works is you look for the MSP. If the MSP is 1, it's negative. If 0, it's positive. So if the value is in positive, it's even the same. So next, the book mean pooling. As I said, it's an average of 4 numbers for data, then divide by 2. So if you see, divide by 4. So if you see here in this design, it's shifted by 2. It's shift 2 times. So 1 time is divided by 2, the second time is divided by 2. So it's equals to 4. So this is what I said before the value part. It will look for the MSP. And this is what the hardware implementation for mean pooling. So please to understand that for this mean pooling, uses the added tree reduction to improve the execution speed. We can use this method also, but it will take more time. So it's always advised to use the added tree reduction. So here from here you can we can understand that each input is placed in R0, R1, R2, and R3. Then it's summed again, then it's divided by 4. Means shifted 2 times. So this is the hardware implementation from the quarters. So if you see here, just now I said that each input is saved in the ROM file, and the output is saved in the RAM file. And then the mean model is where the value and mean pooling happens. The data passes through the mean pooling, the data passes through the value, then the mean. So this is how the mean model looks like. See here first, every data will passes through the value where either it is positive, remain the same, negative, it's 0. Then every time the data passes, it goes to the R0, R1, R2, R3. The next step is summarize. Then the next step is to summarize again. Then shift 2 times. So it's equals to 4. So as I said before, the data from the software. This data is from the convolution. Please do remember that. I didn't take the data I didn't take the pixel value directly from the UNIVERSITI database, but I took the data from after the convolution. So this is what you can see. This is only for one data set. That's around 20 data, same with 400 data. So that's around 20 with the same size but different values. The next part is value. So this is the simulation result from the quarters. So as I said before, what does the value do is positive, even say negative, we can see. So here we can verify from the quarters, the output is accurate. And this is the mean pooling. That's it. Every the 4 sets of data, summarize, then divide by 4. So please do remember this is in hexadecimal, but you can use this value to check with your calculator. You can have the same result. So now compare the software and hardware output. So what I did is the output from the MATLAB, which is the floating point. So what we need to do is change take the MATLAB value using the right matrix function, transfer to Excel, then convert it to hexadecimal. So to make it a fixed point. So then you can compare. You can compare the MATLAB output with the quarters output. So what we should get is every data must be saved. So if you can see here, data is all the same, except for it might increase 1 times or it might decrease less 1 time because of the round off. It might round off to the nearest value that might cause increment to 1 or decrease to 1. But it has no problem on the power function of the architecture design. So this is the result analysis. So this is the third objective, which is benchmarking the performance between the software and the hardware. So we can see here the architecture took around 8050 nanoseconds to finish up its task. There's this is just for one part, but sorry, this is not for one part. This is the whole part, which is for 20 data set. Each data set has 400 data. So you can see here, if we did on the same set of data in the MATLAB, it took around 104458 microseconds. While if you look for the hardware implementation, it took around 8.05 microsecond only. So if you see the difference between the maximum operating frequency for the software, it took 2.6 gigahertz, while the hardware implementation only take a fraction of the operating maximum operating frequency, which is 127 megahertz. So what we can conclude is the hardware is 13,000 times faster than the software, despite using a small operating frequency. So this is the conclusion. This project proposed an interesting approach to address the limitation of software implementation for convolutional neural network, particularly the slow processing speed and high power consumption, which is larger dataset and complex network. By designing a dedicated hardware architecture for application function and meet cooling lanes and energy recognition using FPGA, the project aims to achieve faster processing speed, potentially lower power consumption compared to the software implementation. This is the conclusion what I get from this project. Just before you can see from the performance table, it uses less power consumption to produce the same sets of output compared to software. So a recommendation for the future works. So what I did was for the I designed the architecture for value inputting, but I didn't finish up the entire process of the CNN convolutional neural network. So for the future weeks, um, we need to try to do the, I mean, sorry, we need to try to do the reshape, value, and softmax, and also the convolution. Create the entire uh, CNN model and design the physical hardware. So that's all for me. Thank you.